Alright, so if you skip the last couple of minutes, basically what I did is I just derived this equation here. And so this says that 1 over the concentration of A at any time is equal to 1 over its original concentration plus the rate constant times by time. And so you can derive it using calculus, or you can simply know that as long as you've got a second order reaction, and technically with a stoichiometric equation, A goes to P, then you can always use this expression here. So let's go ahead and look at an example. So let's say we got an amino acid, those are the things that are put together to make proteins. And when you die, one of the things is your amino acids in your body decay, and they form lots of cool molecules, one of which is putrescine. This is a second order reaction, and the rate constant has been determined to be 5.96 times 10 to the minus 4 per molar per second. And if your original amino acid concentration is given, and at some time you've determined the amino acid concentration, then we can calculate how long ago did death occur. Or if you like, how long did it take for this concentration to decay down to this concentration. And so we really just need to sort of plug into the equation above. So let's rewrite that. So that's 1 over the concentration at time t is equal to 1 over the original concentration plus kT. What do we have here? There's our original concentration, so A sub 0. Here's our concentration at time t, A sub t. We're given the rate constant, and so what we're trying to find is t. There's lots of ways to do this problem. I suppose one way we can use some algebra here, and we can go ahead and we can say, well, let's solve for t and then plug everything in. So let's solve this for t. So let's go ahead and bring this A sub 0 term to the left-hand side. Why? Well, that starts to leave t looking lonely. And let's make it completely lonely by dividing both sides by k. And so if we divide both sides by k, then we know that we can calculate t. We just have to take 1 over the actual concentration minus 1 over the original concentration and divide the whole expression by the rate constant. And in our problem, we're given all of these, and so we can just plug them in. So 1 over concentration at time t, so that's 2 times 10 to the minus 3 moles per liter, minus 1 over where we started, so 1 over 3.4 times 10 to the minus 3 moles per liter, and we're dividing all that by the rate constant. Now, the rate constant for this process is 5.96 times 10 to the minus 4, and the units are per molar per second. So we can sort of plug and chug away here, and if we plug and chug away here, what we'll find is that the top of the expression is 206, and the units are going to be interesting. So we've got something that's 1 over molar and then 1 over molar, and so the units are going to be 1 over molar, or molars to the minus 1. And then the bottom, that's just our rate constant, so 5.96 times 10 to the minus 4 per molar per second. Cool, so those per molar, same on the top and bottom, so they cancel out. And then the per second becomes seconds. What's the number part? Well, 3.46 times 10 to the positive 5 seconds. And if you convert that, that ends up being approximately 4 days. And so we can use this to calculate how long it took for the concentration to go down to this particular value. And in this case, it's about 300,000 seconds, or about 4 days. Cool, huh? Now I want to go ahead and talk a little bit about units of rate constants. And I haven't mentioned this yet, but we can develop this idea pretty easily. If we've got a first order reaction, so that's something that's got a rate law, rate equals k times by some concentration to the first power, We know rate is change in concentration with change in time, so molar per second, or of course molar seconds to the minus 1. And if we look at concentration, and since we're not squaring it, it's just got units of molarity, that means that we can calculate the units for a first order rate constant, and all we have to do is get the units on the left the same as the units on the right. And so if the left hand units are molar per second, and the right hand units so far are molarity, then we know that the first order rate constant must have units of per second. Okay, now what happens if you're second order? If you're second order, then that means that we've got a rate law that looks like k times by a squared. And so now, of course, the units are going to be different. Your rate, concentration over time, so change in concentration over change in time has units of molarity per second. Now, if it's second order, your concentration term's going to be molarity squared. And so in order to get the units to come out, we know that k must have units of per second, because so far there's nothing on the right-hand side with time units. But what about the concentration units? Well, if the left-hand side is molar, and the right-hand side so far is molar squared, it's like we overshot. We need to undo one of those molar units. And so it's per molar per second. And if you go ahead and just double check, okay, and if you multiply these out, you've got molarity to the minus 1, seconds to the minus 1, times by molarity squared on the right-hand side. And of course that gives you molar seconds to the minus 1. And in general, you should be able to figure out the units for any rate constant, and it turns out you should be able to figure out what order a reaction is based on its units. And I'll let you play with that at home.